What we have is work kinetic energy theorem that we have seen. First of all, it is going to be applicable in any case, irrespective of the nature of the forces involved. Means whether you have conservative forces acting or non-conservative forces acting, always we can write down net work done to be equal to change in kinetic energy. Okay. So what we can do to get the net work done, one thing what you can do, you can figure out the work done by every force that is acting on a particle, and then you determine the net work done by taking the algebraic sum of the work done by every force. Okay. So one way to figure it out is by finding out the algebraic sum of the work done by each force. There is obvious thing also, no? Or somehow that is not going to happen most of the case. That if you can determine the net force and the net displacement, and using that you can figure out the net work done. That may not be happening in most of the cases. All the cases, most of the time, we'll be doing this only. This is what we have is work kinetic energy theorem. Now, next, what I'm going to do is I'm going to talk about potential energy. Okay, and I'm going to talk about that potential energy in very different manner, not in the way you may find that thing in any book. Tell me, how come someone see getting the intuition or the idea about there must be or there might be something like whatever that kinetic energy is simple or maybe possible because or easily possible because we can say that something moving with more speed will end up having more kinetic energy. Is it not correct? But how come someone would have thought of something like potential energy? What basically it is, object will have energy just because it is going to be at a certain position. So how come someone would have thought of something like potential energy? We will talk about that instead of telling you that this is the definition of potential energy and you mug it up. But in that way, I'm not going to take that. In different manner, I will approach it. So let's see whether it is going to be easy to understand or not. You tell me at the end. So suppose if I have got a case when we have got a force that is acting on the system, which is a function of position. And to keep things simple, I'll consider taking a one-dimensional force, things happening in one dimension. Because one reason is that in math syllabus, we have got only one variable calculus. Correct. So what we have is, suppose if I have got the force to be some function of x, things are happening in the x direction only. So what we can do, the work done in for small displacement along x will be f of x into dx. And so net work done in some finite interval will be f of x dx. And if that is the only force acting on our particle, then the net force will be the work done by this force only. Sorry, net work done will be the work done by this force only. And we know that net work done in any case, we can write it down as change in kinetic energy. So what we'll do, if I'll get the work done by this force when it was at some position 1, maybe some initial position 2 till final position 2, it will be equal to change in kinetic energy, which will be the kinetic energy at 2 minus the kinetic energy at 1. Now what we have got here is some integral with we have to do now. So what will be the integral of f of x? So whatever it may be that function it might be, but on integrating some function of x, we'll be getting some function of x only, not like I'm going to work out of that. So suppose if I integrate f of x, I'll be getting h of x. Okay. And then what I do is I'll plug the limits 1 to 2. What is 1 to 2? Not like x equals to 1. It is the position 1 or the initial position whatever may be the value of the x, and this is the final position. So suppose when I plug the value of the x, whatever I have at position 2, I get this h of x to become equal to h2. And similarly, when I plug the value of the position x, when whatever is the value of the x I have at position 1, I get h1. So h2 minus h1 will become equal to k2 minus k1. And I will rearrange this thing and I will write it down as k1 minus h1 to be equal to k2 minus h2. See, my voice going through, no? No problem. Everything is okay, no? You must give feedback in between. Voice going through properly. No one is having any lag or anything as such because I'm using mobile data. I can't trust that it might be working properly. Okay, then. Now, see, what we have is we got this equation. Nothing is that. Suppose, and if I will write down that there is a function u of x, why I'm doing like that, you will get that, which is minus of h of x. Why I'm doing like that, I want to write down sum of two things to be, so what I have is k1 minus h1 equals to k2 minus h2. So instead of minus, if I would have got plus here, then what I can say, the sum of function k and h at location 1 is equal to sum of function k and h at location 2, correct? Getting the point idea here? Everyone, till here, everyone understood now? Because I'm taking a different approach to make you understand potential energy, which may be confusing for children. Okay, but if I'll not confuse you here, you'll be getting confused in exam. Correct? Till here, all of you got it now? No doubt. Reply once. Aswin understood now? Suraj getting it? Anirudh, Rupesh, there no?
Sir,
Yes,
Yes,
sir.
tell me.
what is the equation you have written after the true
Yes,
box?
sir.
That is, you don't worry about that. That if I got minus in between here, suppose instead of minus I would have got plus, then what I can do, I can write down value of the function k and plus the value of the function h at location 1 to be equal to the value of the function k and h at location 2. Till here, all of you get that now?
Yes, sir.
But we did not got minus there. And whatever, so what I will do, we will define a function which is, see, what is h? It is the value of the, what is h1? It is the value of the function h of x at location 1. So what I will do, I will define a function u of x which is minus of h of x. Okay. So that will do the job now. So what I'll get is u1 will become minus of h1 then, and u2 will become minus of h2 then. So what we can do is I can write down k1 plus u1 to be equal to k2 plus u2. So whatever we were not able to tell earlier, we can tell that thing now. No? That sum of function k and u at location 1 is equals to sum of function k and u at location 2. And we are free to integrate between any 2 points. It's not like we are made to use just point 1 and 2. It can be any 2 points. It means what I can say that sum of k and u at any location, if I'll find the value of the function k and u at any location, its sum will be always constant or not. Or if you're understanding till this point or not. Yeah, we are trying to think how someone would have thought of there must be something like potential energy. It's not like God or something will come in their head and will tell son this is very nice kind of concept, you must know it. Someone would have thought of it first time or not. So what might be running inside his head that we are trying to see. Till here all of you understood or not? I'll give you a moment to grasp it. Or you want to repeat? I'll repeat, not the issue. All of you got it? Amir Khan understood now? Magishwar understood now?
Yes, sir.
Yeah. So understood then good. So now you must have got to know one thing till now that whenever we add You will never find the anyone to be adding like velocity with acceleration. No, we will be adding same things always or not. We never add like tomatoes and buffalo. We'll be adding same things mostly. Correct. So what I have is what is K? It is kinetic energy. So this K is energy sort of thing. So whatever U should be also something which belongs to the species of energy. But what U is, it is a function of X. What is X? We are making the object to move only along X. So what is X? Position. So what U is, it is some energy which is a function of position or not. So what U will be called as potential energy. That is how someone thought of there must be something like potential energy. Till here, all of you got it or not?
Sir, can you repeat it again, sir?
I'll repeat it again. So what we are doing is I am considering having a force which is variable. And what sort of variable? It is one dimensional force acting in the x direction. So what we have got is to change on, we will be changing only things along x only. So, so this force is going to be a function of position and position here is x only. So if I displace the object by very small amount, the work done by that force will be f of x into dx. Along x direction we are displacing, correct?
Yes, sir.
Okay. Okay. So now work done in a finite interval will be integral of this. And this is the only force which is acting or present here. So work done will be just because of this force. So net work done will be the work done because of this force only. And always we can write down net work done as change in kinetic energy. So we are talking in very general term. If I had some force which is a function of x, so we don't know what really that function is. And this f of x, so integral of this thing must be equal to change in kinetic energy. So what I do, I integrate it from some position 1 to some final position 2. That correct. So it will be equal to final kinetic energy, the kinetic energy it has at k minus initial kinetic energy, the kinetic energy it had at 1. Okay, no, k2 minus k1. Now integrating f of x will give us some function of x only. Suppose I got h of x. Then what we do is we plug the values of upper and lower limit. Plugging the value of the x at upper limit 2, I get that h of x takes a value h2. Same goes h of x takes a value h1. So we'll be having left hand side h2 minus h1. Then it is equals to k2 minus k1. Rearranging it, I can write it like that. But now I do some change here. I do some thing here. What I do is I consider assuming a function which is minus of h of x. So whatever u minus of h1 is the value of h of x at location 1. It will become u1. u2 will be our minus of h2. So minus h1 I can replace with u1. Minus h2 I can replace with u2. So that I can write down sum of two things to be always see. What I can do, I can integrate this thing for any 2 points. It can be any 2 points. So what I can say, the sum of the or the sum of the value of the function k and u is equals to sum of the value of the function k and u at any other location. Right now I can integrate it for suppose 3 and 4 next. So I can write down k3. So what k3 plus u3 equals to k4 plus u4. I can integrate that thing for any two limits. So what we can do that we can say that sum of k function and u function at any place will be equal to constant. And what is k? It is the kinetic energy at any position. And what is u? So whenever we add, it must be similar things. No, we cannot add two different kind of things like velocity and acceleration. Correct? And unit and dimension, you must have seen if I have some equation a plus b equals to c. So everyone must be having same unit. Correct? No? So k is kinetic energy. So u must be something which should be having has to do with energy only. So it is some sort of energy only. But what it is a function of x. What is x? It is position. So what kind of energy it is, which is something which depends upon position. That's why it is given a name, potential energy. Understood?
Yes, sir.
Now, when u of x, which is the potential energy function, will exist only when we are able to integrate f of x. Because u of x is minus of h of x, if u of x will exist only when h of x will be present, and h of x we are able to get only when we will be able to integrate f of x. Correct. And now this integral is basically finding out the work done by that force. But suppose if I get some kind of integral which is going to depend upon the path we have taken. So for same initial and final point, I'll be having different values of this integral if I will change the path. So we can't, in that case, we will not be able to write down k plus u to be equal to constant. Getting the point? In that case, we will not be having something that I have, which is potential energy. It means this potential energy function is going to be existing only when the work done by that given force must not depend upon the path taken and what kind of force that we have seen. It is something which is called conservative force. This is what I told you that potential energy function is only going to exist for conservative forces only. Okay, and another thing is that I told you that if you see a force which has got any term to which has nothing to do with position like velocity, time. If you see any term which is not a term of position, straight away that force will be non-conservative. So if I have such kind of force, how come I will be able to integrate that which is going to depend upon more than position? Suppose if force depends upon time also, except apart from position, suppose, then how come I can integrate it? And that integration must be unique for every path I take if the initial and final points are same. You're understanding that point, that integral value must be same as long as initial and final points are same. If it is changing by changing the path, then we cannot say such kind of thing that k plus u will be constant. Now everything is making sense that we have talked about earlier. Now, next is, so what exactly we have done is we have defined u of x, which I'm going to call it as potential energy function, as which is equals to minus of h of x. So what we have is minus of h of x is integral of f of x dx. Okay. Now, next what I can do is, if I have some u of x equals to minus of f of x dx, so if I differentiate something, then integral will be gone or not. Integration is the reverse of differentiation. If I differentiate this side, u of x, it will be d of u, which is going to be minus of that f I'm writing it on as f only, of x I'm writing it on as f only, so f into dx. So what you get is du to be equal to minus of f into dx. And what is f into dx? Which is the small work done in a small displacement dx. So what we get is du to be equal to minus of dw. And what is dw? The work done. By whom? This force. What kind of force it is? That is a conservative force. That's why the thing that is the negative of the work done by the conservative force is going to be equal to the change in potential energy.
Sir, can you repeat again, sir?
See, if I have dy, suppose if I have got y equals to x square dx. So differentiating it will give us dy equals to x square dx. So see, integration is the reverse of differentiation. No, if I differentiate some integral, that integral sign will be gone or not?
Yes, sir.
Correct. Suppose if I have y equals to x square, let me tell you. If I do differentiation dy by dx, what I get?
2x.
2x, correct? So if I
3x
integrate it,
by
so suppose if I have
3
x
cube
square
by
dx, on
3, sir.
integrating what I get?
X cube by 3.
X cube by 3. So if I differentiate both the sides, or this side, what I must be getting? X square or not? Understood, no?
Yes, sir.
Understood or not? So that is what I have done here. that u of x is minus of h of x, which is integral of f of x dx. So if I differentiate, this side will be du, that integral sign will be gone, minus of f dx. And minus of f dx is the work done by our force. What force it is? The force whose work done must not depend upon the path taken. That kind of force is conservative force we have seen. So the change in potential energy is going to be equal to negative of the work done by the potential by the conservative force. And this potential energy function exists when the force is conservative in nature. And why like that? Only when I can write this statement that k plus u will be equal to constant when, or only when the value of the integral must not depend upon the path taken. No? Up till here, all of you understood or not? Because after this, I will tell you in the book is next we will talk about what is reference point and things like that. Or we will talk about each and every different potential energy because of different conservative forces. One thing you can do here is since du I can write down as minus of f dx. So f will be equal to minus of du by dx. Copy this thing everyone after copying tell me. So next class it will we will not have any delay like that. I will fix my internet before the class itself. In the room which were empty, their Wi-Fi was not working. In the room where Wi-Fi was working, that
Sir,
room was not empty. Please tell me.
the next class will be on Friday, right?
The next class will be on Fridays.
Okay.
So next we will see that spring potential energy. Just delay a little bit because of slow internet. Maybe I'll turn off my video. It will help. So what we have is suppose if I have got one and suppose it is already given an elongation x. So the spring force that we are going to have acting is going to be kx. What we have done already, it is given an elongation x in this way, but it is extended by x towards rightward side. So the spring force will act leftward. And what we are doing to pull that spring, every time we are applying a force at the free end of the spring from our side, and we will give a name to it. It is the force applied by external agency or external force. And what we are doing is always we are trying to always we are applying a force which is exactly equal to the spring force. Okay, because automatically on its own the spring will not be able to change itself, or spring force will not appear. Only when we give some change in the length, then the spring force will come into picture. And I want to determine the work done by the spring force. That's why we are applying a force and in a manner such that that force is exactly equal to the spring force so that the end just moves slowly. You may think, sir, if force is equal, then how things will move. We will talk about that also. So if I have got to move something at every point of time, the net force to be equal to zero, then the acceleration will be zero. But that point it can have some speed from the beginning itself or not. So if it is having some speed from the beginning itself, and then afterwards we are applying a force on it in total zero, so still it has got some speed. So it will move with that speed, but that speed will not change. Kinetic energy will not change. So what we are doing is we are just so maybe you might have a block kept on, or I might have some block here is attached to the spring. That way we might be moving. So what we are doing, we are just applying enough force to overcome the friction force. We are not doing any extra other than that. And in doing so, we are going to determine the work done by the spring force. So now, once we are at this position when already it has got a change in length x, and then from there I am going to give a small change in length dx. What exactly is going to be our work done by the spring force? The spring force is acting backward and its magnitude is kx and the displacement is forward. Angle between them 180 degrees. The work done by the spring force is going to be equal to kx dx cos phi. The work done by the spring force came out to be minus of kx dx. Now, what we have got is change in potential energy. So what we know, we don't know potential energy. We know change in potential energy. Why? What is potential energy? U of x, this minus of h of x. What is h of x? Integral of f of x dx. Then what it is? It is the work done. And work done will have any meaning only when we have got some interval. No? Work done at a point will be no meaning to it. So what we know is we know the change in potential energy always. Then from that what we do, we take some reference point where we say that here is our zero potential energy. So what we do in different cases, different way we take the reference, but still where I have selected my reference will not change the change in potential energy for a given interval. I'll repeat that. Wherever you take the reference, it will not change the change in potential energy for a given interval. Why? Because change in potential energy is negative of the work done by the conservative force. And work done by the conservative force will remain same as long as initial and final points are same. Doesn't matter where you selected to call it as u equals to 0 or which is my reference point. Still, we are moving things from same location to final same location. Doesn't matter what path I take, the work done will come same. So negative of the work done will come same. So potential energy will not be changed. The change in potential energy will not be changed, if at all, if I change the reference point. So we are free to select a reference point to be anywhere. Okay. But still, what we do is we select reference point at a place where it will be of some benefit for us. Just a moment. You can hear me now?
Yes, sir.
Just I'll finish this one, okay, now because internet not good. I'm not able to see what I'm doing. I don't know it is getting recorded also or not. You know, so what we have is du equals to minus of dw. Okay, then good. Du equals to minus of minus, it will become plus, no? So minus of kx dx. So what we get is du equals to kx dx. And then I want to write something like potential energy at a point. So now if I integrate both the sides, what limits I need to use is, suppose at x equals to 0, I'll consider, I'll consider the potential energy to be 0. So what exactly I have taken? X equals to 0, I have taken as the reference. So here things are like, okay, only x equals to 0, so everything 0, not a problem. But even in other cases that we'll come across, what I'm telling is, where we have selected the reference will not change the change in potential energy. Well, at that point, change in reference. Reference means the place where we consider u to be 0. will not change the change in potential energy for a given initial and final point, because basically it is work done kind of thing, only just negative of the work done. Correct. What we have, I'll integrate this thing, and next what I do, at position x I will consider potential energy to be u. So now after that easy, only everyone can do the integration and all. So integral of du will be what, u only. So integral of du will be u, limits is from 0 to u, which is going to be kx square by 2. So u equals to half kx square. That is the potential energy because of this. All of you understood now this one? I did not give you the definition of potential energy. It is the energy an object will possess because of the virtue of its position. It's a very bookish kind of definition, but you understand why someone got that idea that there must be something which is going to be potential energy. Okay. Okay then, so maybe I'll end the class here only. So next class I'll keep the things ready beforehand only, that not face this issue. Okay. And don't forget to miss. Don't think of missing the class. Easy only. Just if you come to the class. Then cover this thing.
Next class is
This
on
is
Friday,
still
was
very good
sir.
time. Friday, yes, Friday.
Thank you, sir.
Next class Friday. Okay. Okay then. Bye everyone. See you in the next class.
Thank you, sir.
It has announced no that it is going to start recording. No. Yeah, it's getting recorded. Now, maybe I'll start from the spring potential energy only. So, what we have seen in the last class is that is going to be something you must remember as well. That change in potential energy is going to be negative of the work done by the conservative force. Correct. So, what we know is we know change in potential energy, and then what we are trying to do is we want to give potential energy to a certain location. You get the difference. We know change in potential energy, and I want to write potential energy for a certain position, for a certain particular point. So the moment I want to do such kind of thing, I will have to keep somewhere, or I'll have to fix somewhere to have our reference or not. So that is what we'll see that. So first we will check out the spring potential energy. So what we do here is, suppose if I consider the spring to be having an extension already x, okay, and suppose this side we have given the change in the length, and then the spring force that is going to be acting will be equal to kx, but it will be in opposite direction, is the spring constant. Now from this position, what I am going to do is I am going to give a very small displacement, suppose dx this side. So what we have is spring force this way, and the displacement is going to be opposite to it, angle between them pi. So the small work done by the spring force in having this small displacement will be kx is the spring force dx cos pi. So it's going to become minus of kx dx. Correct. Now what we have is the change in the potential energy is negative of the work done by the conservative force, which is the spring force here. So it will be plus kx dx. And then, so what we see here is we know the change in potential energy, and I want to give some potential energy or I want to figure out potential energy at a certain position. So in that case, we will have to fix somewhere to have our reference. Correct. So what we do is, if I integrate both the sides, when the change in the length is 0, or when the spring is going to be at its natural length, that location we are going to consider it to be our reference, and wherever we keep our reference, or from where we start measuring also, you can say that is something where we fix our that particular quantity to be 0. So at reference we are going to fix, or we are going to have the potential energy to be 0, and then I say the potential energy at any other location at x, suppose u, integrating it will get integration of du will be u, limits is from 0 to u, or maybe suppose if I will not give that thing to be 0, maybe I'll call that potential energy at x equals to 0 as u naught. So integrating u, what we get is u and lower limit u naught, upper limit u. Other side, it is going to give us half kx square after putting the limits. And here what we get, u minus u naught to be equal to half kx square. Now, if I take u naught to be 0, means when x is 0, we consider the potential energy to be 0 at x equals to 0. So that is same as taking u naught 0. In that case, we can say u will be equal to half kx square. So I hope you understood the meaning that we will have to fix somewhere to have our reference. But again, the potential energy is some change in the potential energy is something which is equal to the negative of the work done by the conservative force, and this guy is independent of the path. So since it is going to be independent of path and only depending upon the initial and final position, so in that case, as long as we are going to be starting from same place and then finally reaching the same final location, in that case the work done will be remaining same, doesn't matter where we fix our reference. So it is independent of the path, and so wherever we are going to fix the reference will not change, or the change in the potential energy is independent of the choice of reference. That thing I might have told, maybe I'll just write it down again. Change in potential energy is independent of the choice of reference. That everyone get that, no? We have discussed about it also in last class, I think so. Okay, copy this thing, once you're done copying, tell me, I'll take an place then. Copy, after copying, tell me.
Sir, copied, sir.
Okay then, just a moment. Next, we are going to see gravitational potential energy near the surface of the Earth. Okay. So here you will get more idea about that. What I'm trying to actually make you understand about fixing reference point. So next is gravitational potential energy. Not in general, near the surface of the Earth. And in that case, what we mean, the force of the gravity will be constant and it's going to be mg. Now, what we do again is same exact thing. We make the object to move under the action of the given conservative force, and then we determine what is the work it is going to do for the given interval, and then we fix a reference point to figure out the potential energy at any location. So what exactly one way, another way to, and or what other way you must look at the potential energy is you think of potential energy as a construct, okay, which is basically some method by which we are able to determine the work done by a conservative force. Why we do such kind of thing? Suppose every time, suppose if I am moving from some initial point I to some final point F, so it doesn't matter what path I am going to take, still the work done will come same. Now suppose for this given initial and final point, if I have got defined potential energy, suppose if I have defined potential energy for this given final and initial point, then the delta U, the change in potential energy, we know once, so we can write it down as negative of the work done by the conservative force. It doesn't matter which path we have taken to reach to F from I. Know you're getting that point. So every time we can avoid finding out work done again and again because it will be a repetitive job. That's why we use this method so that work done is going to be same for every path as long as initial and final point same. So why to find out the work done again and again? Why not do something that is the potential energy thing? Understood or not? All of you got the idea why this potential energy is going to be of use here? Correct. Now, suppose if I have a block maybe, and what I'm going to do, I'm going to move this block from the ground level to some height h. And what we do is, since one force, the force that we are interested about here is gravity, will be acting down. So we have to move this thing. So what we do, we apply a force externally. And what we do, we consider this force to be same as mg in magnitude, but opposite in direction. Then you may think, so how this object will move. So it's not like that this object is not supposed to have some speed in the beginning. So it may be having some speed, or maybe in the beginning I will provide some speed a little bit. And then from that point onwards, from which we are going to observe it, we are going to apply a force which is just equal to mg but opposite in direction. So the acceleration will be 0. So it will continue moving with the speed that it was having in the beginning, or maybe small or whatever. So finally, whatever speed it is going to have will be same as the initial speed. So change in speed 0. So change in kinetic energy is going to be 0 or not. Correct. So what we are doing here is, suppose if I write down the work done by the gravity plus work done by that external agency, I'll write it down as work done by WEXT, and that will be equal to change in kinetic energy, which is 0. So what we have is the work done by the gravity is going to be plus work done by the external agent is going to be equal to 0. So work done by the gravity here is negative of the work done by the external agent. There is one thing, but we are not here for this thing, something else. So suppose if I make this object to be displaced by height h. So what we have got is the displacement is going to be upward. So see, even though more than one force acting on our object, but we are trying to figure out work done by the conservative force, which is gravity here. So delta R is going to be h upward. The force that we have got here is mg down. Again, what we have angle between them pi. So work done by the gravity is going to be equal to mgh cos pi, which will be minus mgh. So change in potential energy is going to be our negative of the work done by the gravity. So that will become mgh. Correct. So what is that? Change in potential energy, no man? There is not the potential energy at that particular height. So if suppose if potential energy when it was at the ground, I will write down as U initial. Potential energy when it is at that height, I'll write it down as U final. You get that or not? Because the thing that we know is the way the potential energy we got it is in terms of work done, or what we have got is change in potential energy equals to the work done. Work done will have some meaning only when there is some interval, and the moment we talk about interval means I have to find some change, correct? Change in position even. So the moment we have to do any kind of operation like that, I will have to fix somewhere to have our origin or not. Suppose if I have to measure the difference in the height of two person, somewhere I will have 0 for our scale or not, a ruler or not, correct? Same way you can think like that. The only thing that we know is change in potential energy. Just to give some potential energy to any position, we need to make somewhere to have our reference, and there we are going to consider potential energy as 0. So what we know here is change in potential energy, which will be final minus initial, and that is equals to mgh. Now, if I am going to consider initial potential energy, the one that it is going to have when it was at the ground, is going to be 0 as our reference. So in that case, I can write down the final one to be equal to mgh. So that is what we have here is, when we write down u equals to mgh, what we mean is h is the height of the point object, from the reference. Correct. And every time we are interested in change in potential energy, and that is not going to change if I change my reference. That's why where you fix your reference is not going to do any change in the answer, but still we fix reference in a manner such that it should give us some kind of advantage. Maybe the calculation may be easy if I consider reference point to be at some place. So accordingly, we will select somewhere to have our reference. Understood this point or not? So gravitational potential energy of a point object, we write it down as mgh near the surface of the earth, where h is the height of the point object from the reference. Okay, copy this thing, everyone. Then we will see how to determine the gravitational potential energy of something which is not a point object, maybe some object having finite size, maybe a rod, maybe something else. So copy this thing. Once you have done copying, you tell me. Still, some students are absent. I don't know. Those who will miss classes, for them things will become something that you cannot recover from the damage of missing classes. And getting good college will become almost impossible after some time if you continue doing like that.
Sir,
Please tell me.
so can you again repeat why we make the change in kinetic energy 0?
No, I'm not making it 0, because what we do is we are applying a force on it. What is the force I'm applying on it? External force is exactly equal to mg, but opposite in direction. So net force on the object is what? 0, no? So net force on the object 0. So what we have is acceleration will be 0. So what it is going to have? Initial speed will be same as final speed or not?
Yes.
So change in kinetic energy, that's by 0. Not I'm making it 0. Understood now?
Yes,
Then you will think,
understood,
sir,
sir.
how it will move. So it has some initial speed, but that is not changing. So not changing means
Okay,
kinetic energy will not.
yes, understood.
Understood now? Okay. Magishwar, why you came late, man? You missed some important thing. Check out the recording when I'll share. But recording will be
Sorry, sir.
recording. There's a different kind of mindset when you see something live, no? Correct.
Yes, sir.
Your mind will be present in different manner, I think so. You may ask doubts also. Just I'll repeat since you can follow whatever you can follow till others copy. So here I'm making an object of mass m to be moved to height h, and we are applying a force which is exactly equal to mg but opposite in direction, such that every time net force on it is 0. But don't worry about that. Somehow if I'll make the object to reach height h, then what displacement we have undergone is h upward, gravity acting down. So work done by the gravity will be minus mgh. And we know only one thing, that is writing down change in potential energy, which is negative of the work done by the conservative force. So here work done by mg is going to be minus mgh, so minus of that will become plus mgh. And what it is? It is not potential energy. It is the change in potential energy, which will be final minus initial. So what we know is change. Now, if I want to give some name to certain position, so I must fix somewhere to have our reference now. If I will call 2 centimeter position as 2 centimeter position, means somewhere I have fixed my 0 or not. Understanding the point here? Correct. So that is what we do. If I consider the ground level from where we started moving the sky to be our reference, where we take potential energy as 0, then final will be mgh. So that is what we do. Potential energy of any object near the surface of the earth, a point object, we write it down as mgh. That means h is the height of the object, not from ground, from the selected reference, wherever we may have selected it. And that is not going to change. The change in potential energy is not going to change, since it is equals to the negative of the work done by the conservative force, which will not change because of the change in the reference point, because as long as you start from same point and you reach the same final point, the work done is going to be same only. Understood now?
Yes, sir.
Copy fast everyone. After copying, tell me. Okay, I think I can take a new page now. Okay, I can take a new page now. Not
Yes,
much
sir.
that now. Like suppose if I'll give you a uniform rod. So if I say a uniform rod means it is going to have uniform mass density. So suppose if I'll give you there's a uniform rod standing on a horizontal surface, and I'm asking you consider the surface to be the reference point or reference level where we consider potential energy as 0, and this is a thin uniform rod. So if I say thin, then how much thin? What exactly we mean? Tell me. So if I say thin rod means how much thin? Literally, if we want to think about that, tell me. So it's going to be as thin you can have, because they did not told us how much thin, so how thin it can be. A minimum thickness that will go in Newtonian mechanics is atom thickness. So that much how thin that rod, we must be thinking about that in our head. Now what we know is, we know how to figure out gravitational potential energy of a point object. Here we have got that calculus thing into use. That is not just about physics only, it's going to be used everywhere. So I'll tell you whatever you have to do in general, then I will do it for this one. Now here I have to find potential energy of this rod. So what we do, I will try to think the system to be made out of something for which we know how to find the thing, the one that we have to find. So like the way here we have to find gravitational potential energy, and we know how to find it out for point object. So what I will do, I will try to think our system to be made out of the point object, since we know how to find the gravitational potential energy of point object only. And it is totally okay to consider that we can make a thin rod whose thickness is atom thick by keeping point mass next to each other. Correct. So what we do is, sorry, I'll consider the rod to be made out of infinite number of very, very small strips, each of the strip of very small thickness dy. Understanding what I just told, that I will consider this rod to be made out of infinite number of very, very small strips, each of the strip very small and of equal thickness as well, and so small that each one of them can be treated like a point mass. Okay. So whatever we are going to think the system to be made out of, that is something which is called differential element. So maybe I'll write that point here. So differential element, what it is? If I'll ask you, tell me what exactly or how exactly you will define differential element. So I'll say that it is the mathematical building block. So in reality, everything is made out of atoms and molecules, not that. We are talking about the mathematical building block. So for example, using lines or arranging infinite number of thin lines next to each other, we can make a rectangle out of it. So something like that I'm talking about. So differential element is the mathematical building block of the system. And why we do such kind of thing is because here I want to determine the gravitational potential energy of a rod. And we don't know how to do that. But I know how to find gravitational potential energy of a point mass. And we can manufacture rod by arranging point mass next to each other or arranging them in a line. So that's why we are considering this rod to be made out of infinite number of point masses. And here the differential element for this rod, we are considering it to be a point mass. In this case, understood this point or not, everyone? Money, you have joined now, no? Try to understand whatever you can, otherwise you check out the recorded lecture when I'll share. So what I will do is, I'll consider one such point mass. In general, we have to do now. So I'll consider one such point mass which is at a height y from the reference, and we don't know what mass it is going to have. Suppose the mass it is going to carry is very small, and it is supposed dm. Now, how to find that dm, we'll see later on. But if I'll ask you, can you find the gravitational potential energy of this point mass? That we know the mass, we know what height it is going to be at from the reference. So what we will do, we'll write down the gravitational potential energy of that point mass to be also very small du, and that will be its mass into g into the height, which is y. And now how to find the mass of that element? So for that, you see what kind of mass distribution we have. So we have got a uniform mass distribution. So once uniform we have, then there is something simple like 10 rupees, you get 10 chocolates. So 1 rupee, how many? So same thing I will do here. For length L, the mass is m. So for unit length, the mass will be m by L. So for dy length, the mass will be m by L into dy. Now, like that, if I will calculate the small potential energy of every element like that, maybe infinite, not maybe, there are infinite number of them, and somehow if I can add them up, then don't you think that is going to give us the total potential energy of this rod? Understanding that point? So theoretically, what we are doing is we are thinking this rod to be made out of infinite number of small strips, each one of them of equal length dy, but very small length, such that each one of them can be treated like a point mass. And like that, for every point mass, if I can calculate the gravitational potential energy, and if I will add it up, I'll get the total gravitational potential energy of this rod. But only difference is that we are not going to add it up manually. We'll be using the integration to add it up. So now maybe that example will make more sense. I gave biryani example or not? Like if your mother will cook biryani and then she will ask you that check out how this it is cooked properly or not. You will not eat the entire biryani. You will take a grain of biryani. From that you will decide how that entire biryani is cooked. Isn't it? Same way, we will not be same way the biryani, one grain of the biryani is the point element here. And that one point element we take, for that we calculate, then we integrate it to get what it will be for the whole rod. So there also we test one grain, from that we decide by analyzing in the brain that how it will test when we will eat a plate of it. Understanding it or not? So integration there done by the head, here we are doing it by integration, whatever way. So what we have is net gravitational potential energy will be sum of all the gravitational potential energy of every element, and the sum we are going to do through integration. So it will be integral of dm into g into y. So now I'll replace dm in terms of dy, so it will become mgy by L into dy. Now to figure out for the entire rod, we must plug the limits properly. So how come I can get for the entire rod if I, from where to where rod will be existing? Rod will be existing from y equals to 0 to y equals to L. So we will integrate it from 0 to L, and integrating it simple only, mg by L will come out. We have got y dy 0 to L. Integrating it, you will find it will become mgl by 2. So what we got here is the gravitational potential energy of this rod came out to be equal to mg L by 2. Now we are human beings, so we have got some habit of pattern recognition, not habit, quality of pattern recognition. Now earlier when we were writing it down for point mass, we have got potential energy at some height h from the reference point to be mgh. Now here the mass of our system, which is rod now, is m only. So this is the mass of the system. In place of g, still we are getting g only, but in place of height we are getting L by 2. So there's some pattern or not. What is L by 2? It is the center of our rod now. Correct. So what I will do, I'll tell you something in general that will prove it later on as well, that whenever you come across something which is not a point mass, so what you do in that case, you still use the same formula that you write down gravitational potential energy as mgh, like that thing, you will be written as mgh only, where m will be the mass of the system and h is the height of, basically it is center of gravity. Okay, but what it is I'll tell you now. What it is we'll talk about it later. What center of gravity is, if at all, if the system we have and every point in the system experiences same force of gravity, means if the acceleration due to gravity is constant, throughout the system, and since here we are considering a case which is near the surface of the earth, where we consider itself that g is constant, so that is the case we are talking about here. In that case, what we have is the center of gravity is same as center of mass. What it is, I'm not talking about it now. Once we'll see rotation mechanics, that there we will talk about it. And the center of gravity is same as, in that case, the center of gravity is same as center of mass. So in this case, which is the case we have near the surface of the earth, so h will be the height of the center of mass only. And whenever we have mass distribution which is going to be uniform, if I have uniform mass distribution like the way we have, then the center of the mass is same as geometric center. Okay, so just a moment. So I should complete that statement here. Height of the center of gravity from where? From reference. So wherever you must have selected the reference accordingly. And the center of the mass is same as center of the geometric center. I'll write down center of the mass equals geometric center. So what I mean by geometric center, if I'll ask you, where is the center of this rod? Center only. Where is the center of circle? Center only. Center of rectangle, center of a square, center only. Center of triangle, geometric center of triangle will be centroid, that you know how to find from mass now. So center of the mass is same as geometric center if mass distribution is uniform. So it means whenever you come across a case where mass distribution is uniform in this chapter, and obviously in this chapter everywhere, it will be the case when the system will be subjected to equal gravity at every point on it, means near the surface of the earth. So their center of the mass will be the that will be the height of the center of the mass only. Now, only thing you have to be checking in this chapter is whether the mass distribution is same or equal, uniform or not. If mass distribution uniform, then h will be the height of the geometric center that you know how to find. Next chapter is center of the mass, so there we'll see what center of the mass is, because I can't tell that thing in 1-2 minutes. Okay. And in case if mass distribution not uniform, then you integrate it to figure it out, like the way we have done for this rod. So all of you understood it or not? Gravitational potential energy will be mgh, where m will be the mass of this system, g we know, h is the height of the center of the gravity, which is same as the center of the mass if g is constant, and that is same as the geometric center if the mass distribution is uniform. Okay, copy this thing, everyone. Now we will do one example sort of thing, just to show you how the work done by the gravity is going to be independent of the path as well. Now, but even we know that every constant force will be conservative force. But still, suppose if I am going to take an object to some height h from the ground via this curved path, and we want to prove that the work done by the gravity is going to be same only, doesn't matter what path we are going to take. So what we do is, suppose if I am taking this object, sliding it on the surface, maybe always we are applying a force just to overcome the force of gravity, but doesn't matter. However, we are going to move this thing, just we are trying to figure out what will be the work done by the gravity. Now, what I will do is, I will divide this path into small segments, and then we will determine the work done in one such small segment, and then we will integrate it to figure out the net work done. So let's suppose if I'll consider taking one such a small segment here, okay. Suppose it is some small segment AB, and just I will enlarge it to show it properly what exactly happens. So even though that AB is a curved segment, but it is very small. How small? Atom small. Something which is kind of atom small. So what curve it is going to be? Straight line only or not? Correct. So what we do is that AB, if I take, it is going to be having some angle with the horizontal. Suppose the angle that AB section making from the horizontal is theta. And we are sliding the block on this AB. So what we have is, one will be normal contact force this way, and we have mg sine theta acting down the incline, and we are going to have mg cos theta this way. And so what we have is the force that is component of the force gravity along the displacement is mg sine theta. And what is the displacement that we have got here is AB this side. No? Suppose the segment AB is of length ds. So displacement is going to be ds. So what will be the work done by the gravity? You can tell, no? So the small work done by the gravity here will be minus of mg sine theta into ds. Because this component of the force, so what we are doing is, we are maybe this way also you can think, the work done by the gravity by the component of it mg cos theta will be 0. Only work will be done by the component that will be lying along the displacement. So we are finding out the work done by each of the component of the force to get the net work done. That is also correct thing to do. So mg sine theta acting down the inclined plane and displacement upwards, so angle between these two forces is pi. So what will be the displacement here? Mg sine theta into ds. But if you don't want to do like that, still we have got other way. So our displacement ds acts along AB, mg acting down. No? So what we have done is, this angle is theta, and you can tell this angle will be pi by 2. If I'll apply that same thing, the work done to be equal to F dot S, it will be mg into ds cos of pi by 2 plus theta. No, it is Fs cos theta. So it will become cos pi by 2 plus theta. Everyone knows that or not? Minus sine theta. So it will become mg sine theta into ds. Still same thing only or not? I hope all of you got by both the ways. Okay then. Now next what I will have is, suppose this length AB, however small it is, it will be having some projection along x and along y. Suppose the component of AB or the projection of AB along the horizontal is dx and along the vertical is suppose dy. And this angle, it is the angle which is theta. Okay. So what we have is, in this triangle, we dropped a perpendicular here. Suppose this point is C. So this is dx and this is our dy. So you can check out sine theta in that triangle. I can write it down as, tell me now, dy by ds. So dy will be equal to ds sine theta. So what we can do, ds sine theta, I can replace it with dy. So our dw, which is minus of mg ds sine theta, will become mg dy. Now next you tell me, if I want to find out the net work done, I will be taking the summation of work done in every small displacement ds. So I'll be adding up all the dw. So adding up dw is same as adding up mg into dy. And everyone can tell mg is constant, so can be taken out of the summation. So minus mg, I took it out. Then we have got summation dy. Then what exactly we mean by summation dy? So every small ds will be having its projection in the y direction. So if I will add up all the dy of every one of them, you tell me, if I will add up the dy of every one of them, what it is going to give us? Understanding that point? So adding up, so this is one dy, next dy, next dy. So all the dy added up will give us h only or not, the height that we have got. Understood this point or not? So what we have got, the work done as minus of mg into h. And that will be the work done only or not? Because if I will take the reference to be the ground here, u equals to 0, and the final point will be having the gravitational potential energy to be mgh, and delta u is negative of the work done by the mg. So work done by the mg will be minus of delta u, and change in potential energy here minus mgh. So work done by the gravity will be coming minus mgh as well. Understood this point or not?
Sir, copied, sir.
Okay. Time also almost over. So I'll give you 2 homework to try. We'll discuss it in the class. In case if I have not given it already. What we have is, suppose if I have an ideal string which is pivoted at some point, and what we have here is in horizontal plane. So I'll show you how gravity is acting down. And this is a string of length L, and we have attached a point mass m to one of its end, and it is free to rotate about the point O. So two cases I'll give you. One case, we are applying a force which is always horizontal, and under the action of this force, the point mass is taken to this horizontal position, or it is made to rotate through an angle of 90 degree. Next case, what we do is we are applying a force which is always tangential. You get the meaning of tangential? So this particle will be moving along a path which is going to be circular path. So what we do here is the force is always tangential to the path, and that is how we bring the particle to the horizontal level. Okay. All of you got it now? In this case, the force is constant and always acts along horizontal. And here the force is constant in magnitude, but not constant in direction. It is always tangentially direction. Force is constant in magnitude, but acts tangentially. Just I'll write down, this is my initial position. This is my final position. This is the initial position, and this is the final position. This may be I'll write down as case 1. This I'll write down as case 2. Find the work done in both the cases. So this is one homework. Another homework is that you may not be able to solve, but still you try once. And if you remember, we have talked about polar coordinate that will be of use in here. So what I am giving you is a fixed sphere, and somehow we have kept a uniform chain which is taking up quarter of the circle here, like that, or it is over an angle of 90 degree. So you get that now? What it is? Uniform chain, or even you can consider rope of mass m, and length, you can tell what length it is having. Its length is pi by 2r, where r is the radius of the sphere. So you get that where it is. And this is the horizontal level, or I'll ask you, you consider this horizontal level passing through the middle to be the reference. Find the gravitational potential energy of the chain. So this is also a homework question, and I hope you have done the module solving now. Laws of motion module you have tried now. So please try the laws of motion module, and once you have done that, you read HCV line by line, work power energy. Okay, and no, don't read that. You read circular motion line by line of S.C. Verma. If you understand, good. If you don't understand, still good. You just have to try understanding it. Okay, so try to read the circular motion chapter. It will be before law and near laws of motion somewhere. You check it out. But it will be before work power energy, and try to do the short examples if you can. Okay, so first complete the laws of motion module, then try reading circular motion from S.C. Verma. Try to understand whatever you can understand on your own. If not, totally good, but if you try, that will be very good. Okay, then we'll end the class here. I'll share this thing in our Google Classroom. Okay, then bye everyone. See you in the next class.
Thank you, sir.
Thank you, sir.
Thank you.